Hi everyone. Today we are going to discuss about low spin and high spin octahedral complex compounds. First let us come to octahedral structure. So in octahedral structure there are total 6 ligands attached to central metal ion, and in that 2 ligands are present on x-axis, 2 ligands are present on y-axis, and remaining 2 ligands are present on z-axis. That means total 6 ligands present on the axis only. 2 are on x-axis, 2 are on y-axis, and 2 are on z-axis. And when you come to splitting of d orbitals in octahedral, so these degenerated orbitals are splitting into two energy levels. One is the Eg energy level, next one is the T2G energy level. And how they are splitting into two energy levels means, so in octahedral structure, ligands are present on the axis, and when you come to dx square, y square and z square, these orbitals also present on the axis. So this is the structure of the dx square, y square. These two orbitals are present on the x and y axis, and these orbitals are very near to the ligand. That's why more repulsion will be takes place. Similarly, in case of the z square orbital also, this orbital is near to the ligand. That's why it is also having the more repulsion. When orbital is having more repulsion toward the ligand, so it will goes to the higher energy level. And when you come to the xy, yz and zx orbitals, these orbitals are present between the axis. For example, if we come to xy, so the orbital is present between x and y orbital. And in case of the yz, the orbital is, the lobe of the orbital is present between the z and y. So like that. So in case of the xy, yz, zx orbitals, the orbital lobe is present between the axis and ligand is present on the axis. That's why the distance between the ligand and orbital is little bit more compared to x square, y square and z square. That's why these three orbitals is having the less repulsion, will goes to the lower energy level. That means x square, y square, z square orbitals are having the more repulsion, is going into the higher energy level, and the remaining three orbitals are having less repulsion toward the ligands, are going into the lower energy level. Like that, in case of the octahedral, the degenerated 5 orbitals are splitting into two energy levels. So higher energy level is called Eg and lower energy level is called T2G. So Eg energy is the more and the T2G energy is the less. And the energy difference between these two is called delta O. That is the O is nothing but octahedral. So delta O, that is the energy difference between these. And when you come to the Eg level orbitals, these are having the plus 3/4 delta O energy is high compared to the barrier energy, and x, y, y, z, zx orbitals are having the minus 3/5 delta O less energy compared to the barrier. So this you have to remember in the octahedral splitting, that means Eg level and T2G level. And when you come to this delta value, that is the energy difference between these two, that is depends upon the strength of the ligand. If it is having the strong field ligand, the delta value is more, and if it is having the weak field ligand, the delta value is less. To understand this one, let us come to strong field ligand and weak field ligand. Here strong field ligand, weak field ligand is nothing but, if the ligand is having the more repulsion toward the central metal ion orbital, that is called a strong field. If it is having the more repulsion toward the orbitals, is strong field. If the ligand is having less repulsion, is called weak field. When orbital is having the more repulsions toward the ligand, that means this ligand is having more repulsion, means it will split the d orbitals into larger energy. And if it is a weak ligand, that will split the orbitals into smaller energy. So according to the strength of the ligand, you are having the spectrochemical series. A spectrochemical series is nothing but all the ligands are arranged in the increasing order of their strength. So, for example, if we come to these ligands, iodide, bromide, sulfide, so these are called weak ligands. That means weak field. What is the meaning of the weak field? These ligands are having the less repulsion toward the central metal ion orbital. And when you come to these ligands are called strong field. So that is, if you come to cyanide, cobalt, these are the strong field. That means when these ligands are attached to central metal ion, they will repel orbitals more. That's why these are having the, what is that one, larger splitting, and these are having the smaller splitting. So like that. So depends upon the strength of the ligand, the d orbital splitting will be takes place. To better understand this one, let us come to one example. Let us take a chromium compound attached to fluoride, water, ammonia and cyanide. So fluoride is a weak field ligand compared to remaining three, and H2O is what is that one, strong ligand compared to fluoride. Ammonia is next one and cyanide is last one. That is, cyanide is the highest what is that one, strong field ligand compared to remaining three. So when the fluoride is attached to chromium, the delta value is smaller one because it is the weak field ligand. That's why the energy difference between these two orbitals is less. And when water is attached, the delta value is little bit more compared to fluoride. Similarly, ammonia is giving more energy and cyanide is giving more energy, like that. When the central metal ion is attached to different ligands, depends upon the strength of the ligand, the delta value will be there. If it is attached to a weak field ligand, delta value is less. If it is attached to strong field ligand, the delta value is more. And depends upon this delta value, you are getting a low spin compound and high spin compound. And how we are getting the low spin and high spin compound? Generally, there are two types of the energies are there in case of the electron filling in the complex compounds. One is the CFSE, that is the crystal field stabilization energy. Next one is the electron pairing energy. If the CFSE is less than that of the pairing energy, that compound is called a high spin compound. If the CFSE is greater than that of the pairing energy, that compound is called low spin compound. To understand this one, let us come to different type of the electronic configurations and its electron filling in the strong field compounds and weak field compound. So in that, first let us take the D1 electronic configuration. If the central metal ion is having the D1 electronic configuration, in strong field and weak field, the electron will goes to the T2G level, that is the lower energy. So let us come to, this is the strong field one and this is the weak field one. So in both cases, the electron will goes to T2G and T2G only. Let us come to the D2 electronic configuration. In case of the D2 electronic configuration, two electrons are there. One electron will goes to one T2G and another electron will goes to another T2G. In case of the weak field also same thing. One electron will goes to T2G, another electron will goes to another T2G. And let us come to D3 electronic configuration. 3 electron will goes to T2G only in case of the strong field electronic configuration, and weak field electronic configuration, electron will goes to the T2G only. That means in case of the D1, D2, D3, there is no change in the electronic configuration of the strong field and weak field. But when you come to the D4 electronic configuration, so let us come to first strong field. So in case of the strong field, the delta value is more. In case of the strong field, generally the CFSE is more compared to the pairing energy. So that means in case of these 4 electrons, first electron will goes to T2G, second electron will goes to again T2G, third electron will goes to T2G. And when you come to the fourth electron, this one, due to the more delta value, that means in case of this one, that CFSE, crystal field stabilization energy or delta value is more and pairing energy is less. Due to that reason, next electron will goes to again T2G. So, but in case of the low spin compound, that is the weak field compounds, if we come to this one, first electron will goes to T2G, second electron will goes to T2G, third electron is also goes to T2G. But when you come to fourth electron, here the CFSE value is less, the delta value is less and pairing energy is more. So due to the delta value is less, the electron will easily goes to the EG level. The electron will goes to EG level. That's why it is called I spin compound. So that means the number of unpaired electrons are more. That's why it is called a I spin compound. And here the number of unpaired electrons. In case of this one, the number of unpaired electrons are only 2. So when you come to this electronic configuration, so the number of unpaired electrons are only 2. That's why it is a low spin compound. In case of this one, the number of unpaired electrons are for I spin compound. That means if the CFSE is more, will goes to the low spin compound. If the CFSE is less, it will goes to the I spin compound. That means in case of the D4 electronic configuration, the I spin compound is having the T2G3 and EG1 electronic configuration. In case of this one, the electronic configuration is written as T2G3 and EG1 electronic configuration. And when you come to this one, it is called a T2G4 electronic configuration. Low spin compound electronic configuration is T2G4 and I spin compound electronic configuration is T2G3 EG1 electronic configuration. And let us come to D5. So in case of the D5 electronic configuration, total 5 electrons are there. And in case of I spin, first electron will goes to T2G, second is also T2G, third is also T2G. And when you come to fourth one, same, when it is having the more delta value, fourth electron is also goes to the T2G, fifth electron is also go to T2G. And in case of the I spin compounds, T2G, 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 the three first electron will goes to T2G, fourth electron will goes to EG because the delta value is less and the pairing energy is more. That's why the next electron, that is the fourth electron, will goes to EG, fifth electron will also goes to next to EG. That means in this case, the electronic configuration is T2G3 EG2. In this case, the electronic configuration is T2G5 and it is having the one unpaired electron and it is having the total 5 unpaired electrons. It is I spin compound and it is low spin compound. And next let us come to the D6 electronic configuration. In case of the D6 electronic configuration, easily you can understand the total 6 electrons are present in T2G only. And when you come to a I spin compound, first electron will goes to T2G, second one T2G, third one T2G, fourth one EG, fifth one EG. And when you come to sixth one, again it will come to T2G pairing. So this is the sixth electron. So in this case, it is 0 unpaired electrons. It is having the total 4 unpaired electrons. Let us come to D7 electronic configuration. In case of the D7 electronic configuration, in low spin compound, the 6th electron first fill in the T2G, 1 electron, second electron, third electron, fourth electron, fifth electron, sixth electron. And the 7th electron will goes to into the EG level because the lower energy is filled. That's why next electron will goes to EG level. And in this case, first electron, second electron, third electron, fourth electron will goes to the EG, fifth electron is also goes to EG, and that is sixth electron will goes to T2G and seventh electron will goes to T2G. This is the filling of the electrons in the low I spin compounds. And here it is having the 1 unpaired electron, here it is having the total 3 unpaired electrons. That means when you come to these 4 electronic configurations, D4, D5, D6, D7, the number of unpaired electrons in the I spin compounds and low spin compounds are different. That means in case of the D4 electronic configuration, low spin compounds 2 electrons, high spin compounds 4 electrons. D5 electronic configuration, low spin compounds 1 electron, high spin compound 5 electrons. D7 electronic configuration, low spin compound 0, high spin compounds 4. And D7 electronic configuration, this is the D6 electronic configuration, and D7 electronic configuration, low spin compounds 1 electron and high spin compounds total 3 electrons. And when you come to the D8, D9 and D10, so these are having the same number of unpaired electrons. And when you come to filling of electrons, same. First 6 electron will goes to the T2G, and after that remaining 2 electrons will goes to EG. In case of the high spin, the first 3 electron will goes to T2G, 4th, 5th electron will goes to EG, and the remaining 3 electron will goes to T2G. So what it may be, the number of unpaired electrons same in case of D8 electronic configuration. And this is the D9 electronic configuration, this is the D10 electronic configuration. So in this case, what you have to remember, in case of the D4, D5, D6, D7 electronic configuration, so there is a difference in the number of unpaired electrons in the low spin and high spin. In low spin compounds, number of unpaired electrons are less. In high spin compounds, number of unpaired electrons are more. And let us come to one example. Let us take the COCN6 and COF6. So cobalt when attached to cyanide and cobalt when attached to fluoride. Already know that one, fluoride is a weak field ligand and cyanide is a strong field ligand. So fluoride can split the d orbitals into lesser energy, and cyanide will split the d orbitals into higher energy. That means in the case of the cyanide, the delta value is more. In case of the fluoride, the delta value is less. And when you come to the electronic configuration or electron filling, the cobalt oxidation state in these compounds is +3, and electronic configuration is 3d6. That means the central metal ion is having the total 6 electrons. And in case of the low spin compounds, how the electrons are filling, first electron will goes to T2G, second electron will goes to next T2G, third electron will goes to third T2G, and fourth electron will goes to pairing into the T2G, because the delta value is more. That's why the fourth electron will goes to T2G only, same thing as fifth electron and sixth electron. So all the 6 electrons present in the T2G. The electronic configuration of this compound is the T2G6. The electronic configuration is T2G6. And when you come to high spin compound, the first electron will goes to T2G, second electron will goes to next to T2G, third electron will goes to third T2G. And when you come to fourth electron, when delta value is less, it will goes to the EG level. And fifth electron is also EG level, and sixth electron will goes to T2G pairing. That means here the electronic configuration is T2G4 and EG2. This compound is having the total 4 unpaired electrons, and this compound is having the 0 unpaired electrons. According to this one, you can know the so many types of the properties. For example, when you come to magnetic property, so it is the diamagnetic compound because there is no unpaired electron, and it is the ferromagnetic compound because it is having the 4 unpaired electrons. That means when cobalt is attached to fluoride, it is a ferromagnetic compound. When cobalt is attached to cyanide, it is the diamagnetic compound. Similarly, you can know the color of the compounds also. When the delta value is different, when the lower energy electron is promoted to higher energy, it will absorb the different wavelength light. So when you come to this one, when it is having the less energy, it is absorbed different type of the wavelength light. That means these two compounds can absorb the different wavelength lights. That's why they are having the different in the color also. That means according to the this one, we can find out whether it is a diamagnetic or paramagnetic or ferromagnetic, and what is the type of the wavelength is absorbed by that compound. According to that one, what is the color of that compound. Thank you.